I should thank a lot Claire for the invitation and all the other colleagues such as Olivier, which are making this stay very pleasant. Okay, so as Claire said, this will be an introduction to Hyper-Kählers, and in the other two seminars I'll talk about results of mine and around these things. So, first, let's see what one means by what we mean by Hyper-Kähler varieties. So, it's going to be a compact Kähler manifold is Hyper-Kähler. Let's call it X. If the H20 is spanned by the class of a holomorphic symplectic form. And we ask that X is simply connected. So, example, we can take a quartic surface in P3, smooth quartic. Okay. So this is a two-dimensional example. This is a K3. And in fact, in dimension 2, these are nothing else than K3s. And in fact, in higher dimensions, Hyper-Kählers behave very much like K3s. So sort of Hyper-Kählers of dimension bigger than 2 behave like K3s. This is a general feature. Okay, but for those of you who have never seen this definition, it might seem very special, not something that you would come up naturally with. And so let me state a couple of reasons why this definition makes sense. There is a theorem by Ouvert. I don't know if I should put Bogomolov as well. I'm not so strong on notation. So let's assume that M is a compact Kähler. So essentially, this theorem says that these are among the basic building blocks for compact Kähler manifolds with torsion C1. So maybe I'll just say it not so precisely. So Hyper-Kählers are among basic for compact manifolds with C1 equals 0 in so torsion C1. Okay, the other building blocks being compact complex tori and Calabi-Yau's. Okay, but then there is then these varieties are very interesting from a Riemannian point of view. because let's try and say it just slightly precisely. So X is a Hyper-Kähler, and let's choose a Kähler class. Kähler class. And then by Yau's theorem, there is a Ricci-flat Riemannian metric whose associated class is omega, and G equal Ricci-flat metric. Omega Yau. And then the holonomy of this Riemannian metric is equal to, well, let's say this is, okay, this is the compact symplectic group. Okay, but let's see what does this mean. In particular, this gives a very peculiar consequence, which is very important. And this gives these twistor families. So what that means is that once we have chosen a Kähler class, we get a complex family of deformations of X, so homomorphic family of Hyper-Kählers, which is parametrized by a P1, such that if we look at the Kodaira-Spencer map at this point, which gives us our initial X, so we look at the tangent space at 0 to P1, and we have the Kodaira-Spencer map, which goes into H1 of X tangent of X. And if we use, so now, this is a peculiar fact, we can use this symplectic form. The symplectic form gives us a nice skew-symmetric isomorphism between the tangent of X and the dual, which is omega of X. At each point, it gives us thing. So it gives us this an isomorphism. And so then the image of this map, I don't know, let's call it F. The image of F is the span of omega. Okay, so in particular, this is non-zero, so in particular, we get sort of, usually one gets, by deformation theory, one gets small deformations of X, but here we have a parameter space which is a P1. So this is rather peculiar, and it's a key ingredient in some of the biggest results in the general theory. Okay. And here, just remark for T in P1, very general, the corresponding xt is not projective. Okay, even if you start with a projective x, this will be not projective. Okay. Okay, so now let's look at examples. And okay. So maybe I'll leave this. So so the dimension, of course, is the complex dimension is even. So we start with 2. So these are, as I said, these are K3s. And Kodaira proved that there is a single deformation class. Okay. Now let's give, we want examples in dimension at least 4. Okay. So we have. Yes, he did it. He did it deforming to elliptics. But actually, it's easier. It's even easier to deform to the double curve of P2. Maybe it's even easier. Or quartics. Pardon? No. Because you just in a neighborhood. In any, you start with any K3. In any, of course, you need to know that the deformation space is smooth. No, you can get as they can get. They are. It's like kumas, which are dense. Yes. No. It's purely local. All you need to know really is the deformation space is unobstructed. Kodaira did it deforming to elliptics because he had previously, I think, because he had previously studied elliptic surfaces in such detail that. Okay, so now we look at examples here. So you start with a K3, which can be projective or not. And you look at the space parametrizing zero-dimensional subschemes of a given length or zero-dimensional analytic subsets. Okay. So this is smooth. So this is a Hyper-Kähler manifold. So for example, the simplest example, this is the one discussed by Fujiki, n equal 2. So this is a desingularization of the symmetric product. The symmetric product is singular at points which are, when some of the points have come together. If n is 2, this is the symmetric product. The symmetric square is singular along the diagonal, and you just blow up that, and you get this this thing with straight brackets. Okay, okay. And then Beauville gave another construction of different hyperkählers. You start with, maybe I should move this because it would be too constricted. And what he did is he generalized the classical construction of a Kummer surface, which is a K3. And so now you start with an abelian surface, or even complex toes of dimension 2. And you start from that construction, only you take n plus 1 points, and this, this will have a holomorphic symplectic form, but it will have more than one. It's not Hyper-Kähler, but you can map it to the abelian surface itself by taking a subscheme and mapping it to the sum so this is not a formal sum. This is not an effective cycle. This is really the sum in the group. Okay, and this is a locally trivial fibration in the classical or étale cohomology. And so you look at any fiber. So for example, the fiber over 0. Okay, and he showed that this is a Hyper-Kähler manifold. Okay, and what happens is that B2 of the first example is 23, and B2 of the second example is 7. They both have, this has dimension 2n, this has dimension 2n, but certainly they're not deformation equivalent because they have different second Betti numbers. Okay, and then there are two other known deformation classes. So this denotes the dimension, and so B2 of G6 is 8, and B2 is 24. And for the moment, I listed all the known deformation classes of Hyper-Kählers. So I should say all known deformation classes have members which are obtained as, or are essentially obtained as moduli spaces of sheaves on surfaces which are either K3s or abelian surfaces, so surfaces which have trivial canonical bundle. All known deformation classes have members which are maybe essentially modular spaces of semi-stable sheaves on either K3 or an abelian surface. And then what what I would like to point out is that there's no I mean, there are very few known deformation classes, but there is no I don't know how to say. There is no reasonable even idea of what the deformation classes should be. I mean, there's no even program to so nothing. I mean, which makes yes. Yes, but as far as I know, there's no even a program which might be false, of course, which says that there should be many more deformation classes. I mean, that's what I mean. There's no reasonable, I mean, at least even completely conjectural, but I mean full. Sure. Yeah, I mean, yes, I mean, maybe it's more, yeah, I mean, maybe the natural class are Hyper-Kählers with appropriate singularities. Yes, these are maybe very special. But there's no, as far as I know, even for them, there's no, you know, like, maybe it's impossible to have a classification. I don't know. I mean,
what I wanted in your case, so you were able to construct a frequent resolution, and finally it was clear that it was of a different topological type. But maybe if you allow similarities, it could be a general case that these similar modular species they actually provide new topological models, but without frequent resolution.
Okay, say it again.
No, but I am arguing.
Okay. Okay, so let me sketch some little pieces of the general theory. Okay. So, okay, so I think one can roughly make the usual distinction. So there are sort of some soft results. I mean, not to diminish them. I mean, so what I mean is that you just use general results in complex geometry. And then so here you use, in an essential way, the existence of a Ricci-flat matrix. So you use Yau's theorem. In particular, you use the existence of twistor families. Okay, so let me start with soft results, which are almost the only ones that I'll talk about. So the first thing is that deformation theory is very good. In general, I mean, there's more than one result regarding this. So I'll just mention the first basic result is that Bogomolov says that the deformation theory, the deformation space is unobstructed. I don't know if it's easier, but it preceded. This was before Tian. But it used the symplectic form. It didn't. So it was a few years before. So it's right to call it Bogomolov's. Pardon? Right, but I think probably Yau's theorem hadn't. It was maybe just 1 or 2 years before Yau's theorem. No, it was the end of the 70s. So I think Yau's theorem is the beginning of the 80s. No, end of 70s.
You're talking about history.
Yes. Okay, but it end of 70s. But I think it preceded even. Yes, you're right. So the Twister families, the existence of that Twister family gives an easy proof. I mean, using a very hard result, it gives you an easy proof. Okay. So in particular, what this gives, so the dimension is H1 of the tangent because it's unobstructed, and so this is H1, as I said before, omega of x, and so this is H11 of x, which is B2 of x minus 2, because H20 and H02 are one-dimensional. Okay, so let's look at some examples. So now, if we look at S of K3, the deformation space has dimension, well, okay, so the deformation space has dimension 20, and now if we look at deformations of a Hilbert scheme, in which n is at least 2, then this is 21. So this implies that if you look at a very generic deformation of this Hilbert scheme, it's not isomorphic to a Hilbert scheme itself. So let's call them, so X deformation of N is of type K3N. Okay. And then if we do a similar computation, a very generic deformation of a generalized Kummer, this is a generalized comma I didn't mention, but this is called a generalized comma, is not isomorphic to a generalized comma. Okay, so these are, and these are called, okay, of comma type. So something of comma type is a deformation of a generalized comma. Is that me? No. Yes? Okay. Ah, okay. I should stop speaking or breathing, as you say. So let's put it lower. Okay. So yes. So a Hyper-Kähler of type K3n. In general, it's only a deformation of a Hilbert scheme of a K3, and similarly for a Hyper-Kähler of comma type. Okay, and now let's let's ask a question, and then I'll go on with the general theory. A question which is suggested by these examples. Okay. So the question. Describe explicitly. I never know if there's an E here or not. I guess there is. So describe explicitly all Hyper-Kählers in a deformation class. Okay. Now, since a very generic Hyper-Kähler is not projective, there's no hope. So let's limit ourselves to projective. So the very generic Hyper-Kähler, not projective. So this is hopeless. So let's look at polarized. So in particular projective. Okay. So this is ample line bundle. Okay. And so we want, let's be a little bit more precise, we want explicit, but the emphasis is on explicit. Otherwise, existence, we know since the deformation theory, as I said, is very good for Hyper-Kählers, but similarly, it's very good for polarized Hyper-Kählers. And so in particular, the same computations, similar computations to the one we did before, tell you that even if you start with, say, a polarized Hilbert scheme of a K3, a very generic deformation of that polarized Hilbert scheme is not a Hilbert scheme, and so on. Okay? So we want explicit, otherwise it would be, everything would be reduced to K3s or abelian surfaces and so on, but that's not the case. Want explicit, locally complete families of polarized Hyper-Kählers. Okay? So in dimension 2, so this means for K3s, there are many such families are known. So starting with the sort of the easy cases like double covers of P2 over 6, the quartics, intersections of a quadric and a cubic in P4, and then they're no longer complete intersections of hypersurfaces, but there are many more beautiful families. In particular, they were constructed by Mukai. And now what about dimension at least 4? So one example is sort of perhaps the easiest to describe is you start with a smooth cubic in P5. And you look at the set of lines in Z. So this is a Hyper-Kähler of type K32, and varying Z, you get a locally complete family of polarized Hyper-Kählers. So now there are sort of many other such families are known. And they have sort of, with a sort of intriguing geometry and connection with Fano varieties and so on, but they're always all known examples are of type K3n. Okay, so a challenge is to find such families of the other types, or even some new type. Pardon? You mean a generalized Kummer of dimension 4? Not that I know. No. Yes. Yes, so the sort of the type, Kummer type would be the sort of probably the most approachable. Yes. This is probably the most difficult to find. Okay. And so let's go to another soft result. So maybe I can even give a proof. So maybe it's not a good idea, but okay, maybe I should erase this now. Okay. So another soft result is the existence of the Boville-Bogomolov-Fujiki. So what does this? So X is a Hyper-Kähler, and then the theorem is there exists a bilinear form. So this is a symmetric bilinear integral, indivisible. So when you look at it on the integral cohomology, you normalize it so you don't want it to be a multiple of something, with the following properties. And a positive rational number such that the following holds. Get another piece of chalk. So, well, let me. Okay, so this is sort of a surprising fact. It's telling us so for all. So what this is telling us is that this polynomial of homogeneous polynomial of degree 2n on H2 is in fact a multiple of the nth power of a quadratic polynomial. Okay? And so this is essentially, this is the, it sort of characterizes this up to sign, if you want, if n is even. Once you know this and once you know that, this, assuming it exists, this is uniquely determined maybe up to sign when n is even. But let me list some properties that one wants to know. So this is a morphism of Hodge structures. So 2, 0 only couples with 0, 2, and so on. Yes. What is it? No, you know. Okay. So it's the product of all odd numbers starting from this. So you skip 2 each time. You skip 2. Okay? No, I'm just normalizing so that it becomes. I think that normalization should be there usually. It's convenient when you write out. When you this factor is convenient when you take the polarization of this polynomial. Why? Okay, because this is equivalent to the integral over x of alpha 1 cap alpha 2n equal to cx times, okay? So you take all products, but you avoid formally equal repetitions in this summation. And so if you don't put the double factorial, then you have to. Okay? So you have an equality between these two polynomials. So from that, you can get the unique multilinear symmetric function, which when evaluated on the same, that's the polarization, which is this, and the polarization on the other side is this thing. This thing. So they're equal. Okay. Let me write down. So this is a morphism of Hodge structures. So again, that just means that H11 only pairs with H11 and so And then there is a sign. So statement, if omega is a Kähler class and sigma is a holomorphic symplectic form, then what we get is that if we restrict to the span of I shouldn't write sigma. So what I want is this. I want to restrict to sigma and h20 of x intersected with the real cohomology. So these will be all, oh, I'm sorry. This is omega. I'm sorry. So this restriction is positive. And instead, if we restrict to the real H11, this is negative. Okay? So I'm taking the span of the Kähler class. And so this is wrong. Okay, I'm sorry, this is wrong. This is the perpendicular. Okay, this is wrong. Intersected omega perpendicular. This is negative. So, okay. So here I should just put sigma plus sigma bar where sigma runs through H20. So this is a three-dimensional real vector. So I'm restricting this quadratic form to the real cohomology, and I'm saying that it has signature 3 comma something, but I'm being more precise. So if you restrict it to the span of the Kähler class and the real part of holomorphic 2 forms, this is a 3-dimensional space, you get positive definite, and if you restrict to the real H11 part perpendicular to the Kähler class, you get negative definite. Okay, in particular, it's non-degenerate, and of course, so example, if X is a K3, of course, this is just the intersection product or on H2, of course, and if X is a deformation, of course this is okay, then if we look at the integral, so of course you can, since it's an integral, bilinear symmetric form, by restricting it to the integral cohomology, you get a lattice, so a free finally generated group with a bilinear symmetric form, and this is isomorphic to U3 and then there's a piece which is -2 to the n minus 1. Okay, so so that means in general it's not unimodular. It's non-degenerate, but in general it's not unimodular. And so for some reason, in all of the known examples, this quadratic form is even. But even this, I mean, it would be, maybe there's some elementary reason why it has to be even, but I've never seen any. Okay. Maybe there is some. If one could know something more about the Bogomolov-Fujita quadratic form in general, a priori, it would be useful. Okay. Now, now I have a choice. So. So in the way I've written it here, in the known examples, it's always an integer, actually. So of course here it's 1, but here it's 1, here it's n plus 1, and I'm not so sure about these, so I think these are the same, if I'm not wrong, are the same as sort of what you think of these as. I would have to check about these, but I think they're. Okay. Now so maybe let's try and oh, but this happens periodically. I mean, I didn't change. Now I've understood. Okay. Probably. Okay. Okay, so let me try and give a proof. To show you that the existence of this quadratic form is quite powerful. So, so we have Matsushita theorem. So X Hyper-Kähler, and we assume that we have, so these are hypotheses. We assume that F is surjective, connected fibers. Let's assume that B is normal. Let's assume it's projective. Okay. Then, and I don't want B to be a point because I can't say anything, and I don't want to have the same dimensions of X. Then the dimension of B, let's say X has dimension 2n, the dimension of B is exactly half of the dimension of X, and then all fibers have dimension the same as the generic fiber, and the fibers are generic fiber, the smooth fibers, is a complex torus Lagrangian. And then there's some other things. B looks like Pn, and this is B smooth. This is actually B equal Pn. This is a result of 1. Okay? So one has a lot of information. So I want to show you just this first fact. Let's So this follows easily from the properties of the Bogomolov quadratic form. So since I have just 2 minutes, I'll panic. I better read. Okay. So let's prove this. So let's say HB is the pullback of an ample class on V. Okay. And but that's the trick. No, you can't. Okay. And let's see what we can say about this HB. First, HB is different from 0. This follows because this is scalar if you look at a fiber and so on. Okay. So if you intersect with itself HB, the number of as many times as the dimension of B, that is homologous to a positive multiple of the fiber, and that's non-zero because you have a Kähler class on X. So the pullback is non-zero. Okay. But now, if we compute the Bovil-Bogomolov form here, it is 0 because we know that this, if we compute HB to the 2n, this is 0 because we can first, this is the same as pulling back HB to the ample class to the 2n here, and this is 0. But this, on the other hand, is Cx time. So this means that this has to be equal to 0. Okay? But now, assume, now we want to prove that the dimension of B is exactly n. So first we assume it is less than n, then we assume that it is bigger than. So assume that the dimension of B is less than n. Okay? Then HB to the n is equal to 0. Okay? But now, since this quadratic form is non-degenerate, there exists a class alpha in H2 of X such that alpha HB is different from 0 because HB is not 0. And now we compute, but now the integral over X of HB with itself n times, well, this has, then we couple with alpha n times. Okay, this is 0 because this is 0. But if we apply the formula we had before, well, we had that Cx times that sum tilde in which we couple together all possible ways. So if we couple HB with itself, we get 0. So the only non-zero contributions are we couple HB with alpha and times HB with alpha. So that means that we get some multiple which is non-zero of HB alpha to the n, which is different from 0. So we get a contradiction. Okay? So this is not possible. And then then we do similar kind of thing, assuming it is bigger than n. Okay. This would give you this, which I just proved. Yes, you're right. Yeah, but why? Okay, so why are they Lagrangian? Okay, so you take you take the okay by type. Okay. Yes. But now, okay, let's, but that doesn't work with this other, no? Because here we assume the dimension of B is a D where D is bigger than N. Okay? Okay, so then HB D times is different from 0. Okay. And then we take omega x equal Kähler class on x, and then if we compute x d times, and we compute this omega x, the remaining number of times, so 2n minus d, this is different from 0 because we're just taking, this is represented by a positive multiple of a fiber. And then this means that we're just integrating the Kähler class as the maximum number of times on that fiber, so it's a positive number. This integral is positive. Okay? Yeah, it's the Zariski closure, yes, yes.
And it is very clear that along the quadric, you have the relation alpha to the n plus 1 equals 0.
Sure, sure. Okay, but you're, okay. But I'm, okay. But I'm deriving it formally from those properties. Yes, yes, sure. Yes, yes. Yeah, yeah, sure. That's going a bit deeper into the proof. But here you just apply that, that polarization formula, and so you have to, so this is this Cx times this sum, and what you have to couple, choose two of these classes, couple them together, and so on. But the fact is that if you couple HB with itself, you get 0. So, and since there are more HBs than omegas, you will have to couple at least HB with itself once, and so you get 0. So this is 0. So you get this contradiction. Okay, so I won't mention, I mean, of course, I won't talk about hard results because the time is over. Yes.